Okay, here we are. As you know, this is the last lecture of this course, unless you have other lectures with Professor Ceola, I don't know, but okay. In the room, they tell me that it's already gone, also her part. So basically, today is the last lecture for the full course, and then we will see each other for the exam, of course. And you know that the first call is December 22nd. I think I'll be able to schedule it in Almesami very soon, because I need for the approval of the exam commission. It's just a formal requirement by the master degree program coordinator, and I think they are going to approve it next week. So at the latest, at the end of next week, you will see the call in Almesami, along with the other calls for January. And as I mentioned to you, the room for the call, for the first call, will be here in Ravenna, in this building, via Tombesi dell'Ova. The exam, as you know, needs to be taken in physical presence. And the room for the next calls will be communicated to you later, because before booking the room, I need to see how many people will take the exam on the first call, and then we will agree the details for the other ones. Of course, during this period, from now to December 20, I'll be available for any clarification by email for sure, December 22. By email for sure. So if you need any clarification, please send an email. And if needed, I'm also available for virtual meetings. So again, let me know if you need any virtual meeting. I think we already discussed also the structure of the exam. I anticipate that today in the afternoon, I will also tell you some information about possible questions in order to give a further contribution to improve your understanding of how the exam will be. I don't think it is a problem, and but of course, I'm willing for any clarification you may need later on. A last thing, I will publish very soon a call for getting the survey of students' opinion, and it will be online. So you are kindly requested to fill the form of the evaluation of the teaching during this course. This is particularly important, and it is particularly important because I'm very keen on receiving suggestions from the students, first of all, and second, it is particularly important because also the university needs your feedback in order to understand how it's possible to improve the teaching, the quality of the teaching. This is particularly relevant because this is a new curriculum, as you know, and therefore it's particularly important that we get your feedback. And I may also kindly ask you to give explicit suggestions, and I explain how you can provide them. So first, you will get instructions for compiling the survey link and the code by email. I will publish the advice on Teams and on the forum in Virtuale. So you will get an email and a message in the Teams chat, like, please fill the form at this link here, use this code. And the code allows you to enter into the form. The form, as you know, is completely anonymous and is composed by two parts, essentially. There is a first part that is closed answers, like the exam, like the quiz of the exam, and the second part where you can include suggestions and criticism in text boxes. I think it is useful that I explain how this information is used. So the first part, closed answers, is statistically analyzed by the university. And it is basically the part that the university uses for evaluating the quality of the teaching. And these numbers are used according to a statistical interpretation. And these numbers are used only if the number of students, the number of field forms is greater than or equal than 10. So it is unlikely that we get to this number this semester, this first edition of the course. So the university probably will not use these numbers because a statistical analysis is not possible, as you know better than me, with a small sample size. If the university could use it, this would be used in order to allocate resources to the departments and in order to confirm the master degree program or to give a lower priority to it in order to make future plans. The university doesn't use these numbers in the first part to evaluate individual professors, but still the evaluation of this first part is extremely important because once that is statistically analyzed, the outcome provides information on allocation of resources. And basically, it's your decision to decide whether the master degree program should be continued or improved, if it is continued, or discontinued. Of course, in this case, this is the first year we will not reach the number of students required, so the university will not use these numbers, but still, it's important that you fill it. Second part is, to my view, even more important because the university doesn't look at the comments, basically, and the comments are forwarded anyway to the teacher. And this is, for me, an important information because, as you can understand, it is useful advice on how to improve the quality of the teaching. You may suggest additional topics. You may suggest to discard some of the topics. Usually I get from students the suggestion, please discard probability, but unfortunately, this is a subject, climate change, where we cannot discard probability, but you could say, for instance, please try to teach probability in a different manner with a different approach. And it is important that you expose your criticism, extremely important, and because criticism is the most important thing of it. On the other hand, it is also important that you express your appreciation, if any. Usually students think that appreciation is implicitly recognized if they don't write anything in the box, like if I'm not expressing any criticism, it means that I am appreciating it. So this is unfortunately not good because indeed, if I don't see anything there, it's like not participating at the elections. I still don't know your opinion. So if you appreciate it, it's important that you write. A sentence is fine, like I like it, stop, full stop. It's no problem, but still it's a clear sign. If you have criticism, of course, try to be detailed because I need to understand what is the matter of concern. I understand that in your case, you are few students only, so anonymity is not fully preserved because it's clear if we get 5 field forms, you know, it's not like getting 200 of them. So it means that anonymity is not fully preserved, but you have my full assurance that I have a positive intention. So I'm really keen on receiving criticism, and this has, of course, sorry if I say a trivial thing, doesn't have any effect on your exam. It doesn't have any effect also because I am receiving your comments after about 6 months. So this is why the university is taking a delay because it wants to give you the time in cases like this one to take your exam without the teacher knowing your opinion on the course. By the way, if you are willing to share with me any individual comment or entertain a discussion on what you liked and you didn't like, this is perfect. So you can just send an email and we can discuss by email, or we can meet in physical presence. For instance, after taking your exam, you may want to say something. This is fully perfect. So this is basically the essence of the survey. Again, you will get an email asking you to fill the form. And I really would appreciate if you took the effort, given that you are few students only. I think it is particularly important. I mean, when one has 200 of students, it's no problem if 10% don't fill it. In your case, 10% means of 5 means one person, and therefore even missing contribution, even a single one, is a miss. It's indeed a miss. Okay, I think we can move forward now with the lecturing, and we are talking about decision theory, and you see the link on the web page. You see, I want to stress once again, the links in red were not discussed, and also the last one will become red probably, okay? Design of climate change adaptation actions probably will become red because I don't think today I have time to deal with it, okay? But let me decide at the end of today. And so the red ones, please feel free to discard them. My advice is take time to read them because I think this is useful information to complete your CV. It remains, the links remain there for the very reason that I think it is useful information. So my advice, take the time needed not to study them, but to read because they are very easy. Particularly the first one, climate change and water, is very long, but it is very easy to read. The second one is a bit more technically short, is a bit more technical, but still I think it is an interesting reading for an engineer. So let's then focus on decision theory once again, and I want to make a brief recap, but to make the brief recap, I refer to the PowerPoint presentation. Just let me take the web page to the point where we are starting, Infogap, but then let me go to the PowerPoint presentation, which is here. So we got to discuss robust decision making, and robust decision making means selecting a decision, selecting an alternative that is not necessarily the best one in terms of reward, but it is a robust alternative. Robust, as we said, means that the decision, the strategy, is robust against failures of our design, of our evaluation of the benefit provided by an alternative. When I say it is robust, it means that even if our design fails for some reasons, the damage that we get is not a big damage. So it means that if, for instance, we have to design to adapt to climate change by installing air conditioning, and we may, into the buildings, we may get a prediction that the future temperature is +1 degrees with respect to now, and then it turns out that actually the future temperature will increase of 1.5. So it means that our design was erroneous for the presence of uncertainty, not because we made a mistake. We know that there is uncertainty, and we know that the design, the forcing that we have accounted for may be erroneous. And therefore, taking a robust solution means that our project of air conditioning doesn't fail completely if the future temperature will increase 1.5 instead of 1. We may decide to install an air conditioning apparatus that can be updated. This means that the cost of installation is larger. So this means that we select a solution that is not the optimal one in terms of benefit, because maximizing the benefit would imply that I take the solution that is less costly in terms of installation. Instead, I decide for a solution that gives less benefit, but In case of erroneous design, temperature plus 1.5 gives to me the opportunity of adapting, which means that the planned benefit will be probably anyway achieved, or it will be achieved with a very reduced penalization. If I had taken the optimal solution, maybe it turns out that the benefit is zero, and therefore seeking robustness means giving up to the max benefit for the sake of getting safer with respect to uncertainty. This is the definition of robust decision making. Then there is an approach that is indeed called robust decision making, and it's codified. We discussed it a little bit. And robust decision making, the approach called robust decision making, is articulated through an analysis of scenarios. So it means that I identify alternatives, okay? So like different apparatus of air conditioning, and then I evaluate the future climatic scenarios. So I don't rely on a single best estimate, but I admit for uncertainty, like I account for uncertainty by using 10 different climate models, 10 different predictions, and then I generate 10 different scenarios, and I try to understand what happens if one or the other one of them materializes. And in doing that, usually, we don't look at probabilities, because we cannot really identify what is the probability of the best model. So we just rely on the fact that each scenario is possible, and therefore we explore what happens, and then we may select a solution that is not the optimal one, but it is a solution that through updating or through other strategies allows me to get anyway a benefit if something goes wrong, okay? So let's, this terminology of calling robust decision-making a specific approach includes some confusion. So we may talk about, in general, robust decision-making, which means that we go for a robust solution. And we may have different approaches for seeking a robust solution, and we will explore what they are. And one of these approaches is precisely called robust decision-making. So there is, I mean, the terminology is a bit confusing. And so let's don't get confused and make a difference between robust decision-making in general, which includes different approaches, and the approach that is called robust decision-making, okay? Perfect. We didn't go into the details of robust decision-making. We only went through the steps, okay? So we discussed the steps. And you see that you can recognize here what I just said. Identification of future scenarios, system models, and metrics to evaluate success. Metrics to evaluate success. One metric can be the benefit, the economic benefit, but there could be other metrics, like comfort of people evaluated in some way. And then candidate strategies are identified. I would say that the identification of candidate strategies is the first step, okay? And then we use the future scenarios, which here have been previously identified, in order to test the candidate strategies. Look, there is this approach is called bottom-up. I mentioned to you that we can also classify decision-making approaches into two big categories, top-down and bottom-up. Bottom-up is like a buzzword today. There is a great appreciation for bottom-up approaches. What's the difference? Top-down means that I start from the modeling of climate. I start from my predictions of climate change. And then I test different alternatives in the face of my predictions. What is the difference? What is the potential problem here? Suppose that you have very pessimistic predictions, which turn out to be wrong after 50 years. But suppose you have just a pessimistic prediction of future climate. Then, when you take into consideration the strategies, the solution, you may reject strategies that look not enough effective, because in the face of the scenarios that you produced, you see that a strategy is not reaching the goal. Okay, so you may, again, for the example of air conditioning, let's suppose that your scenarios predict a future increase of 1.5 or more, and then you select the apparatus, the appliance that gives to you the possibility to cope with at most 1 degree of increase of temperature. You reject it, okay? But if in the future scenario turns out to be plus 0.8, you rejected an alternative that was indeed the best one. So this is the downside. The positive thing of the top-down approach is that it's very clear and relatively easy, because you see that it's very easy to download climate model predictions. It's very easy to take the most pessimistic one, SSP 8.5, business as usual scenario. This is what also the European Union, by the way, recommends. So take the worst scenario, it's very easy, and with the worst scenario, you make your prediction. It's very, as I said, very easy, okay? And, you know, it's also very easy to be communicated. And this is also the reason why the European Union recommends it. I mean, you have several predictions, take the worst one and get prepared to it. The inconvenience is that, you know, a lot of resources are needed because you start from pessimistic predictions. Bottom up means, in this case of robust decision making, that the climate model prediction are used not as first step, are used as second step. So first you identify solutions, and then you use the climate model predictions to check if the solutions are effective. And in doing this switch, in putting evaluation of solution up front, there is actually a big change in mindset. You could say, but practically, from the point of view of an engineer, it's the same thing. No, it's not the same thing, because you put up front identification of solutions. You discuss them with the stakeholders, and then when it comes to the evaluation of future climate scenarios, this is the second step. It's the less uncertain. You put in the second, you put as first step the less uncertain, because identification of possible solutions, there is very limited uncertainty. In climate scenarios, there is a lot of uncertainty, and therefore, to start with the less uncertain information is a big change of mindset in a decision. So, again, this robust decision making is called a bottom up, because actually these candidate strategies are decided first. Okay, this is what we discussed of robust decision making, of this kind of approach. We didn't provide any example, and we didn't provide any quantitative details. We didn't say what metrics could we use, etc. Now, let's go to where we stopped the last lecture. This is a second method, which is also a robust decision-making approach. So we can call it robust. It's part of robust decision-making in general, but it is very different from the specific method called robust decision-making. Of course, they show some similarity. The problem is the same problem. You have climate change, and you have to adapt, and you have different solutions in the face of uncertainty. So there is similarity. But here, as I summarized last week, there is an important difference. It's still a bottom-up approach, as we will see. And the important difference is that instead of deciding after an estimate of uncertainty, we revert once again the decision. We identify solutions and metrics to evaluate success, and we investigate what is the max level of uncertainty that still allows a satisfactory strategy. So I evaluate the different strategies, and for each of them, I can get an estimate of the max level of uncertainty that each strategy can tolerate. This is a first difference. So uncertainty is not quantified beforehand. Beforehand, we quantify the max level of uncertainty which I can tolerate. And in the face of robustness, the larger the uncertainty, the better is. Because, of course, I may prefer a solution that is working, even if uncertainty is large. So I may prefer a solution that tolerates uncertainty, tolerates a larger uncertainty. And another big difference is that InfoGap also evaluates the possibility, as I mentioned last week, of getting an unexpected reward. And keep in mind that uncertainty, as I discussed last week, can be an opportunity, because uncertainty means that your prediction, if it was a pessimistic prediction, may turn out to be wrong in the sense that in the future you will get more than what you expected. And indeed, InfoGap recognizes that we should also evaluate the benefit that may be given by uncertainty. And look, in this case, the reasoning is opposite with respect to the previous one. When I evaluate unexpected rewards, I look for the minimum uncertainty that looks an unexpected reward. So I try to repeat the concept. If I'm looking for a risk, to minimize a risk, I'm looking for a solution that seeks for the max uncertainty. I'm looking for the solution that can tolerate the max uncertainty because I feel safer. I mean, I can say, okay, my prediction will be wrong, no problem. The solution will work anyway. So when I'm seeking robustness against the risks, I look for the solution that can tolerate the maximum uncertainty. When I look for a solution that may provide an unexpected reward, I am looking for the solution that may produce the reward with a limited uncertainty. So, I mean, of course, if I have a solution that gives a benefit only if my project is plain wrong, it's not very interesting because, of course, I try to optimize my project and it is unlikely that it's plain wrong. Instead, if I see that a solution may produce a reward, even if my project is uncertain but to a limited extent, it means that I have a larger probability of getting this reward. And therefore, I may prefer the solution. But of course, I have to look at the trade-off of these two components. I will provide to you an example, a numerical example, because to give you an idea. So I have to look for a trade-off, because of course, I have to look for robustness, but also I have to look for the unexpected reward. And I mean, I need a quantitative evaluation of the pros and cons. So unexpected reward, robustness. And this is a nice idea of this method, as I said, because it also looks for unexpected opportunities. So I think here we already discussed this, okay? And what I just mentioned is summarized in this slide. And I think that now it's nice to provide an example. First of all, yes, there is a question. Yes.
This strategy is safe.
is safer if the solution can tolerate a high level of uncertainty.
It means, for example, our safety factor is higher.
It means that if you decide for a solution and this solution is working for a large range of possible design variables, this is, it means it's not a question of safety factor. So, I mean, if I select a solution that is more or less the same cost, more or less the same benefit, but it can work for a larger range of future outcomes, this is better, okay? And instead, if I look for the reward, I would like to seek a solution that may provide the unexpected reward, even if I have a very slight change of the future. Because I'm not expecting in the future this large uncertainty in order to seek a reward, because otherwise it's not worth seeking. I mean, if I make a prediction of the future and the reward is very unlikely because you need a very large uncertainty. Large uncertainty means that it's unlikely. So it's not very interesting. But I think the best thing is to provide an example. But first, let me clarify how this method quantifies uncertainty. And it quantifies uncertainty for a given variable, design variable, by defining a range. So, and the range is increasingly larger. So, like, I make a prediction of future temperature and uncertainty could be plus minus 10% of my prediction. And this is a range of uncertainty, which I explore. And then I increase plus minus 20%. So I explore the range. And then I see to what extent of this expansion, the solution can work anyway. And this is the way it quantifies uncertainty. And then this is applied for both seeking robustness and seeking the unexpected reward. Okay, let me provide, first of all, there are three essential components of this method. It's a decision making, so you can recognize that these components are quite trivial. The model, which reflects our understanding of the system, and with model, I mean the model that allows me to estimate the performance of the solution. So it can be an economic benefit. And I'm not meaning here the climate model, okay? Because I'm not really now looking for climate prediction. I'm not really involving climate predictions here. The model is the model that evaluates the performance. It's the model of the system. Like, for instance, air conditioning. So a model that expresses the performances of the air conditioning system. And then the performance requirements. So basically, what is my target? I want to resist to an increase of temperature of plus 1.5. This is a performance requirement, okay? Or could be the performance requirement, could be economic benefit. I want to gain at least 1 million. And the model allows me to estimate the economic benefit, but it's a different thing. The model gives to me the estimate, and then I have to set my performance requirement. So a performance requirement may be, as I said, I want to get at least 1 million. If there is no 1 million gain, then it's a failure. And I have also to, I come to your question in a second. I have also to fix what I mean as an unexpected reward, like 2 millions. If I get to 2 millions, this is really good, okay? So I have to set a minimum and a target for reward, unexpected reward. Your question. Yes, good. Yes, it depends on the metric that you decide to use to evaluate success. Okay, so success typically in an industrial endeavor is money, is the rating of the investment, for instance, the financial rating of the investment. But the performance requirement could also be to save at least 10% of people who are now suffering or from heat waves, okay? And then we need an uncertainty model. And I already specified that here I don't use a specific model, I just quantify uncertainty with increasing ranges, because I'm just interested in quantifying the maximum level of uncertainty that can be tolerated. Let me see if I have the example here, and I think we can anticipate the example. Okay, so let's make this very simple example. X is the future uncertain prediction of water volume in millions of cubic meters that is annually managed by an irrigation board. This is a very relevant problem. Okay, when we talk about climate change adaptation, a very striking challenge is irrigation, because we foresee, the models tell us that low flows will be reduced in many continents. Actually, the observations still don't confirm that in many cases. In some of the cases, yes, they confirm. But for instance, in Italy and in Europe in general, there is no clear evidence that low flows are decreased from the data. But the models tell us that they will decrease. And this is a striking challenge because, of course, irrigation is related to food production, is related to the water-food energy nexus, etc. And therefore, let's refer to this example. So we know an estimate for the future value of X. Again, X is the water volume in millions of cubic meters in a year. Okay, that is available. And we have an estimate, but we know that the estimate is uncertain. And let's suppose that we have also an estimate of the deviation of the error of our uncertain prediction. And let's call it with the letter S. And let me just use also the blackboard, because only at the slides it's not really the best thing. So let me pin the blackboard. Yes. Okay, good. Now we're almost there. Okay, so, and then we can look at the screen. Sorry, I need also the screen. Okay, good. So again, I have X water volume. Okay, water volume. And then I have a prediction. The prediction is called X up. We have a prediction X up. It's not yet on the screen. You will see it later. Okay. And then we quantify uncertainty with an estimate of a deviation, which we can call S. S is just a qualitative estimate. It is obtained in some way, but we know that it's not really precise. Okay, and we also need to consider what happens if the future value X, let's call it future value, X may be much lower than X minus X hat minus X. Okay, this may happen. So I have to consider it. Okay. And let's not talk about probabilities, because if I had a probability associated to S, this would be a quantitative knowledge of uncertainty, and I don't have it. Okay. Now, I need a model, as I said, to quantify the performance. The model is on the blackboard here. Okay. So what is the B? B is the, let's call it the time. Okay. and can be an economic benefit. Fine, it's no problem at all, because we can use economic metrics to evaluate success of a strategy. Let's not be in a way too politically correct, because some people say, no, let's not talk about money, but debate you on what, I mean, we are engineers, we need a metric. So it's fine if the metric is economic success, okay? Because it means that people used it, people ate the food, and therefore that's fine. So this function that you see over the screen, Ex, is equal to, you see, an initial value B0, correct? Okay, plus B1 minus B0, which multiplies 1 minus E, it's an exponential power of minus x. So this is a typical remote function in water resources management. It means that if you depict it into a graph, here, the graph is next slide, okay? Let me just anticipate it for you. It means that if you have here on the horizontal axis x, and on the vertical axis you have bx, it starts from an intercept that is b0. You see that if x is 0, this is e to the power of 0 is 1, this becomes 0, okay? And therefore, the benefit Ex is B0, okay? It starts from B0 here. And asymptotically reaches B1 with a pace that is dictated by the parameter K, okay? So this is our benefit function. Asymptotically going to B1, and the pace of convergence, the rate of convergence is dictated by K. And this model has 3 parameters, B0, B1, and K. Okay? It is a model that we need to estimate, and you know that it's uncertain. Maybe uncertain in B1, uncertain in B0. So B0 may be 0, for instance. You have an estimate for B0, but it may be like 0, okay? Of course, this is a benefit that is greater or equal than 0. You cannot, I mean, you also have a negative benefit, but let's assume that it's, because if it's economic, it may also be negative, but let's assume that it's only positive here. Okay, so you have this reward function. Let's see if next slide in a bit. You see, and this is for values B0 equals 0. Let me see if it's written here, no. But in this case, clearly B0 is 0. X is expressed in millions of cubic meters of water volume. And it seems like the asymptotic value is 16. And the benefit is expressed in millions of euros. And in the web page, the parameter is not important. Okay, I'm not plugging in here. And let's go back a little bit to denote with the symbol beta, with the symbol. I use the x hat, let me use x tilde as an optimal benefit. I realize now that I use the tilde. Okay. So let's denote with b tilde the estimate, the best estimate of my benefit, which corresponds to x tilde. Okay, so again, I have a prediction of future x, which I call x tilde. And of course, this is b tilde is my best estimate of my future benefit. Okay, so it will be like, for instance, here x tilde, like here x tilde, and then I go up, and then I get here my b tilde, b tilde, sorry. Okay, because I have a prediction of future x. But there is uncertainty, okay? Good. So this is a function. And now let's introduce the uncertainty model, okay? And the uncertainty model is defined as you see here. So basically you define a range x minus x tilde, and x is a possible outcome. It's a possible future outcome, okay? So when I look in the future, I realize that it is x as true value. And there is a discrepancy, a difference with respect to x tilde. I divide this discrepancy, this difference, by my previously estimated error, possible error, and then I obtain my uncertainty model, which is indicated here with the symbol H, UH, sorry, UH. What is H? H is a limit that I can put on uncertainty. So I decide H, like, I want, let me define a first level of uncertainty. H is 1. If H is 1, it means that my uncertainty model says that my future predictions are in the range dictated by S. If H is 1, it means that the max discrepancy between prediction x tilde and the future value is equal to S. Okay? If here x minus x tilde at the numerator is equal to S, I divide by S, I obtain 1. Okay? And so it means this is an uncertainty level, like my solution, my strategy allows me to tolerate up to a level H of 1. A second solution may allow me to tolerate an H up to 2. So you understand that, but a second solution may give a different benefit. So it is interesting for each solution to try to identify what is the robustness to uncertainty. And you can identify the robustness in this way. So first of all, look at for a given value of H, U identifies a range. U is a range, okay? Because here again, if you fix H equal to 1, U is a range, and it is the range of the possible future outcomes that differ from x tilde at most of S. Okay, so U is a range. U identifies a range. So now we need to quantify the robustness of the solution with respect to uncertainty, with respect to this range. And how can we identify the robustness? So let's look at the scene. Basically, you have let's look at the screen and let me write it in the blackboard. Because I mean, what I'm saying conceptually is very easy, but the notation is a bit heavy. It's like when starting probability statistics. Sometimes we're talking about very simple things, but then the notation becomes a bit heavy. So it is extremely important that you try to follow the reasoning by looking at the concept. So we got to the stage where we define a level of uncertainty H, and for a given H, I obtain a range of possible future value of X. So basically, when I define H, I define a range in UH, which includes possible values of X. Remember that here, S is fixed, X tilde is fixed. So when I change H, I change the possible future values of X. Okay, and this UH is the range of the possible future values of X. Perfect. Now, let's pass to the next step. I need to clear the blackboard. And what is the next step? Is to measure robustness. To measure robustness. And let me start from what you see in the center of the formula. X in the range UH. So let me look at all the possible values of future water volume inside UH. For any possible value of future water volume, I can compute a benefit with the benefit function B0 plus B1 minus B0 multiplied by the exponential, okay? And then I compute all the possible benefits. And here there is only B, perfect. B actually depends on X, okay? I could add here Bx in order to clarify it. And I look at the minimum. I look at the minimum. Okay, the notation is a bit different. I don't have parentheses here. I want it to become equivalent to what is on the screen. So let me remove the parentheses and put the minimum here. Okay, minimum. Again, so far, I think it is easy to follow. So I get all the X in the range in range. I compute for all of them the benefit and I look for the minimum. Why I look for the minimum? Because I'm seeking robustness. So I am exploring all the possible futures. And given that I want robustness, I want to look at the worst case. You may remember we also talked about the min-max method. It's more or less similar. I look at the minimum, and then what I now want is that this minimum is the maximum possible. Okay? So you see here now I take parentheses, and then I look at the H with I look at the H. Remember what is H? H is let me just go back a little bit to the slides. H is what defines the range. Okay, so I look at the maximum level of uncertainty. H is the maximum level of uncertainty. I look at the level of uncertainty which gives a benefit that is greater than a critical value. Okay, and then I said I want the maximum level of uncertainty. So I get here just max critical value bracket max. So I look for the max level of uncertainty, which defines a range that I explore of possible X values. Inside this range, I look for the minimum benefit, and I want to make sure that it's greater than a critical value. So I am looking for the maximum level of uncertainty that gives to me the opportunity to get success. And this is what I call H hat, which depends, of course, on the critical value that I fix to the value. I mean, the reasoning is exactly what I anticipated by words. So I'm looking for, once again, I fix a target, a mean benefit, to declare that my solution is satisfactory. And I look for the maximum level of uncertainty, I call it H hat. I look at the max level of uncertainty, which gives to me, anyway, for any possible future outcome, a value that is satisfactory, is larger than a critical value. Now, this is probably easier to be understood if we now realize that we could make a graph of it. So we could make a graph showing on the vertical on the horizontal axis B critical, okay? Or let's say on the vertical axis, on the horizontal axis there is B. We can show here B critical, and here H B. So let's see if I use the same symbols. And I think at this stage, we need also to specify these parameters, okay? Because this is basically the graph, which is the benefit in millions of euros. And here, actually, it is, let me just anticipate the structure of the graph, and then I tell you the parameters. It's a benefit in millions of euros, which depends on the level of uncertainty, okay? And in this case, let's look in this, because it's we see here, okay? This is the version with the symbol, uses the same symbols, and then I explain to you later the structure better. But I first need to use the parameters, and let me go, because let me see if they are given here. And let me first unpin the blackboard. Okay. Good. And let me look at the next one. Okay, the next one is further consideration. So let's go here and let's look at the parameters for this graph. Okay. Let me see. Robust expansion parameters are not given here. And, so they are given in the exercise. Sorry, I didn't remember that. They are given in the exercise because there is an exercise provided in order to repeat this. Anyway, what I may say is that we have prediction of 24 millions of benefit. So if we look, let me just go here. Okay. So basically, we have a best prediction for the future of X, which leads, which I don't remember what is the value of the best prediction. You have to go into the exercise in order to repeat it. but gives for the best prediction of this a benefit of 24 million of euros. So this means that if I get an X value that corresponds to my prediction, which means that uncertainty is zero, because if the future value of water volume corresponds to my prediction, it means that my prediction model was correct. And therefore, I have to assign to this prediction uncertainty zero. And the resulting estimate is 24 million of euros uncertainty zero. When I increase the uncertainty, of course, I have to look at all the possible X values inside the range, estimate for them the minimum benefit, which will be lower than 24, because I'm starting to look for values that of X that are lower than the best prediction. That I get, when I increase the uncertainty, I get a lower benefit. So this graph, which is called robustness function, gives me an idea for the problem that I presented of what is the lose in benefit if uncertainty increases. And then we get to a value of zero benefit for uncertainty that is represented by an H value of 2. The H value which is dependent also by from S, which is my initial estimate of uncertainty. Okay, so working on the equation that you see on the blackboard, I can start from the best prediction, uncertainty zero, compute the related benefit, and then starting to see what happens if I don't get the expected prediction of water volume, but I get less of it. And therefore, given that I get less of it, the benefit decreases. And of course, I may fix here a critical value of the benefit. So here I am exploring all the possible values of the critical benefit. But let's suppose that I need at least to get 5 millions. I use this function, 5 millions, I go up, and I see that I can tolerate a level of uncertainty up to 1.8. Let's suppose that my critical value is 12. I decrease the robustness. And then I can here, and I see that I can only tolerate H to 0.6. H to 0.6 means that my initial prediction S of uncertainty is larger. Because remember that my initial prediction corresponds to H1. So basically, up to H values that are from 0 to 1, I am working in the domain of what I am expecting based on my estimate of uncertainty. But if I exceed 1, I'm going out of the domain. So basically, if I want to get at least 20 million, this is the max level of uncertainty that I can tolerate, which is lower than the domain. And therefore, okay. Instead, if my mean is 10, I see it tolerate up to H1.4, which is more than certainly expected, which is fine. Okay.
So and S
sorry?
the S is less in this one.
Yes, yes. S is in this case, it means that S is less, yes. And also, one thing that you can recognize that the steeper the sky, the better it is. Okay? Because if it was steeper, instead of getting it into a max of 2 or 0 benefit, I could have gone to a max of 6, which is fine, because it means larger than certain. So this robustness function, basically, by looking at all the possible future outcomes and quantifying the benefit for the minimum benefit for all the possible future outcomes, gives me an idea of the robustness of the solution. And of course, this is for one solution. Then you may look to another solution, it's a steeper curve, and then you may select the other solution. Okay, now let me now look at let's look at another interpretation from now, and the other interpretation is the expected luck. When I discussed this card just now, I said, let's explore what happens if I get less water. And then we have an increase of uncertainty, because increase of uncertainty, I wanted to look at the minimum benefit attainable for all the possible values in the face of uncertainty. And of course, I look, given that I'm looking for the minimum, I look at all the possible values of water availability lower than the expected. Okay. But indeed, uncertainty means that if we didn't get more water, I didn't cross so far this option of more water, because I'm looking for the minimum. I'm looking for the worst outcome, and therefore I only explore less water than predicted. So remember that this corresponds to zero uncertainty. It means that it corresponds to my prediction, zero uncertainty. When I increase the uncertainty, I can get less benefit, which means that I get less water. But uncertainty means that I could also get more benefit. Now let's explore this. And so it means that I have to expand this graph on the right, because I'm getting more water. And therefore I'm expecting that now I need an additional curve that starts from the point where the blue curve finishes. Okay, the blue curve finishes at zero uncertainty with a benefit of 24. Now I'm looking for another curve that starts again from zero uncertainty, benefit of 24, this is the same, but looks for more water, additional minor, because I get more water. And what I get is a curve like this one. And look, now you see the definition here. It's a dual definition with respect to the previous one. A dual definition because now I'm looking at the minimum of the maximum. Look here, I was looking at the maximum of the minimum. But now I'm looking at the minimum of the maximum, exiting again including the range. And then I also need to insert somewhere here this value BW that defines the expected minimum. BW, which of course is larger than the And here now we start to see that there is that critical BW, where I want to be actually this bank, but I could locate them here. And here you see that now there is an increasing benefit. I think there is not much more to say about this. I think it is enough that you notice that there is a different notation for used, and then there is a dual reference to minima with respect to the previous equation. Now, also this graph is part of an exercise that you have in now. And this graph is called opportuneness function. So you have the combination between the robustness function and the opportuneness function. Once again, remember these graphs refer to a specific alternative. And then we may have a different alternative with different curve. Okay. 1 second, I want to make sure that I am included in the camera. Here we were. Now, for the same reasons why I would prefer a blue curve that is steep, here for the red curve, I would prefer a gentle slope, meaning that I would prefer a larger increase of benefit for increasing uncertainty. And then what I have to do is, okay, let's see the trade-off between robustness and opportunities. And this comes to the domain of the discussion that you may have with stakeholders, like, okay, this, let's define the critical value to ensure success. And so, for instance, let's define a critical value of benefit of 15. Okay. And so let's define a critical value of the benefit of 15. This means that I look at the blue curve, I can tolerate up to an age of 1.1. And with this level of uncertainty, what is the benefit of the unexpected reward corresponding is not really so large. And so maybe lower than the BW that I defined as something that may be interesting. And therefore I may say, okay, let's look for something that is more robust because, of course, if I increase robustness, I also decrease the unexpected reward. And therefore, I may decide for something that is more robust and a solution that gives a different trade-off. Okay. And this is something that needs to be discussed typically with your stakeholders. You define the critical value of the benefit, and you define what is an expected reward, and then you decide what is the level of uncertainty that you may decide to tolerate. Like, because if you increase uncertainty, of course you increase the expected reward, but you decrease also the critical value of BW. So for instance, here, if you fix a level of uncertainty of 1, an H of 1, you end up with a risk that is quantified by a critical value of 16, and an unexpected reward that is quantified by something like 29. And then you may decide, for instance, in this case, okay, let's try to get a solution that gives to me more safety because the unexpected reward is not really so attractive. Okay. This is basically the concept of this method. And let me just show you the parameters now. Okay. And in order to do that, I have to go back to the web page here. Oops, sorry. It's here actually. And the exercises. Where is it? Okay. computational risk associated to. It is another one. Okay, I don't have the link here, so I will check the parameters and give them to you in the afternoon. Because I think it is interesting also to look at the parameters that I used for getting these pictures. And the final consideration, this picture, I think, are not using the correct notation. I noticed it now, and I will not have time to change it in the short term, but I want to discuss with you why I'm saying this. Because here, I should have written benefit B, H, or B, or beta benefit in general, not critical benefit and unexpected reward, because the value of the critical benefit is to be fixed on this horizontal axis depending on my choice. But the title, the caption of the horizontal axis should be benefit, not critical benefit, because the critical benefit is not given here. Okay? What is varying along the axis is the benefit. Okay? And I need to make a correction of this. It's just a correction of the caption. It's not for the remaining part, it's fine. Okay, let me just share some consideration with you. So, opportuneness function and robustness function confirm that robustness is the greatest uncertainty that gives the required outcome, while opportuneness is the lowest uncertainty that enables us to aspire to an unexpected windfall. And the trade-off is interesting. When you look at these pictures, it's indeed the trade-off which is interesting, which gives to you the opportunity to decide if you are willing to accept more uncertainty in the face of unexpected opportunities. And another consideration, what is the zeroing property? This is an interesting consideration. It is called the zeroing property, the fact that this card converges to the estimated value of the future benefit for zero uncertainty. This is something that we discussed earlier. So I have a best estimate of X, which gives a best estimate of the benefit. But the best estimate is subjected to uncertainty. If I materialize the best estimate, it means that I got zero uncertainty. Okay. Now, what this is called the zeroing property. So these curves are zeroing to the best estimate for zero vertical axis. Okay. What does this mean? If you look at this best estimate, it's not robust. So it means that when you are in the presence of uncertainty, it is not a good option to take the best estimate and making a project with respect to the best estimate. So you have a model, like maybe a climate model, maybe whatever. You have a model that is subjected to uncertainty that gives a prediction. If you adopt this value of the prediction to drive your project as an input variable as a design variable for your project, you have no robustness against uncertainty, which means that for sure you will not get that benefit. Maybe that you get more, maybe that you get less. There is no robustness. Instead, if you design with something that is lower, you get some robustness against uncertainty. Okay? And you get a corresponding uncertainty, indication of uncertainty. It gives you the opportunity of getting as an unexpected reward. So the moral of the story is that this complicated theory brings us to realize something that maybe you say is trivial, it's naive, but brings us to realize that in the presence of uncertainty, we should never work with the best estimate because there is no robustness. It is very unlikely that we get what we are designing. This is indeed something interesting. And look, why I said this may look to you naive. This may look to you naive because we are engineers and we know that we need safety factors. And the reason why we need safety factors is precisely the fact, and then we come back to your question, we need robustness. A safety factor means robustness. And indeed, let's say that this approach allows us to estimate quantitatively the robustness of a safety factor. So if you instead of designing for 24 million benefit, you design you divide by 1.5, you take a safety factor of 1.5, which means that you design for a benefit of 17, more or less. So it means that if you take a safety factor of 1.5, you get to a robustness level of 0.8 or 0.9. Okay. And you may say something like, why do we need this complication of, I'll go back a little bit. Why do we need this complication of this uncertainty model? Wouldn't it be better to ignore this and just work with a range? Answer is yes, it's possible. And they decided to work in this way because they had to solve a problem where they had indeed an estimate of uncertainty, which was, however, deemed to be not reliable. And that they wanted to compare with this estimate of uncertainty. They wanted to get in this graph a number that was more understandable. For that, it means that if I get one, the uncertainty corresponds to my estimate. Okay, and but indeed, you may wonder why this complication? Because I could work with a range, and I could put in this graph the range. Yes, on the other hand, they decided to work in this way because they thought that it was more practical. In general, when you look at models, design models, in this case, we are discussing a model for decision making, keep in mind that it's just a possible solution. So there are other solutions. And the InfoGap is adopted this representation because they had to address a very specific question. And this is a method that is only 25 years old. So it's not really something that has been then generalized, modified. Okay, good. And let me see. Yeah. Yeah. Expected reward, yes. Okay. When I wrote over the blackboard with the variable x field, my best estimate of, in this case, future water resources availability. So I have a model, like hydrological model that gives to me a future prediction. This model is uncertain, but the model gives, of course, a best estimate because it's not a model, you get a number. Okay? And then this is the number, and you can compute your expected derivative benefit. That's not about derivative. We need the benefit. So basically, this is the expected reward because it corresponds to the expected prediction of water resources. And this is in my conclusion, just a few minutes ago, was if you take this X field as designed, it's going to go some more considerations, and then we make the break. The lack of robustness is particularly concerning when you cannot quantify uncertainty probabilistically, because if you have indeed something reliable of uncertainty quantification, then you don't really need to look for safety factors because you decide your safety factor probabilistically. I mean, if uncertainty is reliably estimated, you decide your safety factor looking for probabilities. Like, for instance, when you design bridges, and the law recommends that you get a rating period of 200 years, which is related to a given probability of not exceedance, because you understand that if the frequency is on average of an event 1 over 200 years, you also determine the frequency and then the probability. The law gives to you the safety factor in terms of probability. So basically, the law is considering uncertainty in the estimate of river flow and tells you, I want a safety factor that corresponds to a probability. Then in this case, it's less needed the robustness. It's already given by the probabilities. You reason in terms of probabilities and you decide your robustness level. But if you know that there is uncertainty and you cannot quantify it probabilistically, then it is useful that you look at all the possible outcomes without assigning probabilities, like it is done here. They look for the minimum without looking at probabilities. Just keep in mind that when you work with environmental problems and environmental models, we all know that uncertainty is an essential information, but it's not always possible to get an uncertainty estimates in a quantitative way. So, for instance, with climate models, they provide an uncertainty estimate in terms of envelope of ensemble simulations, but we cannot assign a probability. And therefore, it is particularly important that we explore the possible outcomes and maybe that we consider that there could be something more than that uncertainty. And therefore, this is why basically I have the need of exploring what is the maximum level of uncertainty that I can tolerate. Look, in climate science, this approach is not really liked because if you explore increasing ranges of uncertainty, then you may include in the range the option of no change. Like if you look for air conditioning and you explore increasing ranges of future temperature, you may, by expanding, include the option 0 increase. And this is something that in climate science they don't like very much. And so it gives to you the opportunity of considering the no change option. If you start from down, you don't consider it. You look at climate predictions and you don't look at the no change option, because climate models, all of them predict change. And all of them predict usually a very bad change, a very negative change. If you start from the bottom-up approach, you may consider alternatives that work and produce a benefit if there is no change. And then you may use climate models only in the second step. But indeed, if in the first step you see that there is an alternative that gives an unexpected reward for no change, then it may become interesting to you. Like, okay, the models say that this reward will not materialize, but if I see that with the minimum level of uncertainty in these models, it can materialize. So if I see that a minimum level of uncertainty in climate model predictions gives to me the no change option, why not to consider it? it could give an unexpected reward. So it's an approach that is not usually liked in climate science. Usually in climate science, when you talk about bottom-up, they prefer to start from the models because they think it's more precautionary, which is reasonable. I mean, I'm not questioning.
We cannot change.
We cannot change option. And if this is possible with, it's compatible with the prediction of climate models, I can realize that it's compatible because even a limited uncertainty of climate models could give no change. Then it's interesting. I mean, we shouldn't exclude as engineers the option that climate in the future will not change anymore. This is possible. We shouldn't exclude the option that temperature starts going down. Of course, according to the model predictions, this is very unlikely, and there is no model that predicts if you don't decrease the CO2 concentration, there is no climate model that predicts temperature may go down. What could be the reason why temperature goes down? Decrease of solar activity. And there is no model considering such a possibility. Why? If you look at the literature, there is some literature supportive of these natural fluctuations of solar activity, which may compensate the increase of CO2 concentration in the atmosphere. Just keep in mind that it is bad if the temperature will increase. But even if we predicted today a decrease of temperature of 1 degree at the global level, so going back to the pre-industrial level, it would be a big problem. Because in the pre-industrial level, it was a completely different world. It was colder. It was completely different world, adapted to a temperature that was 1 degree less, and in some locations it was 2 degrees less. So people were equipped in Venice, in Rome, to deal with the snow, with everything. Now, if we got a decrease of 1 degree temperature from today to tomorrow, which is impossible, of course, it would be a big problem because we would be completely snowed and with no possibility to cope with it because now we are not used to that. So, I mean, okay. And then I think we can continue in the afternoon. Thanks a lot.